So besides LLE or locally linear embedding, there is another nonlinear dimension reduction method, which is known as Laplacian eigenmaps. In fact, both LLE and the Laplacian eigenmaps were published in the same journal issue in Nature, and they were independently developed into different research groups, but with very similar essential ideas. But their mathematical formulations are indeed different. So for Laplacian eigenmaps, indeed, they did construct the k-nearest neighbor network or graph. And instead of using the kind of reconstruction formulation to derive local reconstruction weight matrix, W, they are going to compute the distance in the original feature space. Essentially, this Wij measures the k-nearest neighbor similarity. And then what you are going to do is to say that after the nonlinear dimension reduction, the reduced representation Y's, their distance are going to capture the locality or local neighborhood relationships in the original input space. So how did they make sure that they come up with this loss function? So I want to minimize this weighted distances in the reduced subspace. And this weighting is dependent on how similar those corresponding input feature vectors in the original space. So that's kind of Laplacian eigenmap formulation to derive the reduced representations. So this Wij is computed based on the k-nearest neighbor distances. If k-nearest neighbor distance are very similar, then k-nearest neighbor distance are smaller, then W is higher. And if they are not belonging to the k-nearest neighbor distance for each other, then W is equal to 0. So you don't need to worry about how far away of the reduced representations. So that's a formulation. And why the authors call it Laplacian eigenmaps. The reason is that if you rewrite this loss function in matrix formulation, if you do some algebraic manipulation, then you can write it as this Y transpose D minus WY. This D is essentially the diagonal matrix adding up all the similarity measures for corresponding rows. And the W is essentially this k-nearest neighbor similarity matrix, as we explained. And if you put it in the graph theory, this D is actually known as a degree matrix, and D minus W is the graph Laplacian. So when you are trying to minimize this loss function, essentially you are trying to find the corresponding eigenvectors of the graph Laplacian corresponding to the eigenvalues of the graph Laplacian matrix. So that's why this is known as Laplacian eigenmaps. In fact, this Laplacian eigenmap dimension reduction algorithms is also related to one of the clustering algorithms, which is known as the spectral clustering algorithm. So essentially, after you derive the reducer representations, you can apply the k-means clustering on those representations to achieve the clustering. And this is why eigenvectors of the graph Laplacian matrix as a spectral representation for graph relationships. And we will not talk about the spectral clustering algorithm when we talk about the clustering algorithm, but just remember that the Laplacian eigenmaps actually derive the spectral representation for the k-nearest graph data, and then you can apply clustering algorithm on those reducer representations to derive the groups of similar data point in the original feature space. And in fact, there are many extensions of LLE and the Laplacian eigenmaps. For example, UMAP is one of quite commonly adopted nonlinear dimension reduction algorithms. So one of important modifications that UMAP did is that when they construct the k-nearest neighbor graphs, they need to make sure the k-nearest neighbor relationships are mutual. So in the Laplacian eigenmaps or E, when you're looking for the k-nearest neighbors, actually for the specific data point, you only find the k data points which are closest to this data point in the original space. But for UMAP, basically what you need to do is if certain data point, instead of having the k closest distance, but if this specific data point is not the k-nearest neighbor for the other data point, then you do not count it as the k-nearest neighbors. So that's one important modification people are trying to use, because similarity relationship should be symmetric. Using The Laplacian eigenmaps, there is one example doing segmentation. In fact, basically we're looking at the pixel value features in this image as well as the distance of each pixel to each other, and then use those features as the original input feature vectors, and then you do the construct the k-nearest neighbor and do the Laplacian eigenmap, dimension reduction, and then trying to do the k-means clustering here. Basically, you implemented spectral clustering algorithm, and then you can see that it can identify the corresponding corner regions in the given image.